Last time I finished with a lemma 431, right, which was a discussion about what the exponential function looked like. Right? So basically, for cardinals, exponentiation is a bit of a black box. Sort of indicates that you know what's inside the box, or somebody knows what's inside the box. Cardinal exponentiation, nobody knows what's inside the box, and nobody knows exactly how this works. So there are a few things that we can say, and that was we mentioned in lemma 431. Let me put it up again here. So recall that we defined the cardinality of what we defined we defined capital lambda, cardinal exponentiation. We defined this as the size of any collection of functions so where f is a function and f takes L to k, where we've prearranged some L of size lambda, cardinality lambda, and a k of size kappa. So this is how we defined cardinal exponentiation. We looked at the functions from sets of the appropriate size with a domain of size lambda, range here in size kappa. We look at the collection of all these functions. We look at the cardinality of that set. And we showed it made no difference which L's and K's you chose. All that mattered was they had the right size. So it only mattered that they had the correct cardinalities. Of lambda and kappa. That was exercise 430. We then showed 431 up here. Okay. If I take cardinals, kappa could be finite, but kappa is less than or equal to the infinite lambda. Then all of these sets were bijective. So a set of functions from lambda to lambda, right, is bijective with a set of functions from lambda to 2. And this we identify, we can biject that, if you like, with characteristic functions of subsets of lambda, which we went through last time. So in terms of their cardinals, each of these has the cardinal below here. These are all equal. So this is one thing that we can say about cardinals. And we're just about to do another lemma that says further things that we can say. Right? So this will be lemma 432, right, which is over the page. So this will be some basic rules of cardinal arithmetic. So capital lambda plus mu is capital lambda times capital mu. So again, this just mirrors what happens with finite. Right? 2 to the power 3 plus 5 is 2 cubed times 2 to the 5. We just add the exponents. And we've done an earlier exercise that's going to help us through these things here. So, well, I'll write the second one up. We'll do them both. Capital lambda to the power mu is capital lambda times mu. So again here, 2 to the 3 to the 5, right? It's the same as 2 to the 15. Right? So again, it just mirrors what happens with finite. So we look for what happens with 1, and the proof refers back to rather a lot of lemmas during the course of its development. So we've done exercises or previous lemmas to kind of set this up. If you look back at 415, look at 415 too. If I can get the thing to focus. Here we had a bijection between the functions from a union of two, well, assumed disjoint sets, x and y into z, was bijective with the functions from x to z, the Cartesian product y into z. So we're going to use that here. Right, so that said, if I got x union y into z, this was bijective with x into z Cartesian product y into z. If I had x intersect y with disjoint. So let's use this. And actually, I'll use this with x and y being lambda and mu themselves, right? So these are perfectly good sets of cardinality lambda and cardinality mu, respectively. So I'll use those rather than just some abstract L and M. Likewise, Z I think of as the set kappa itself. Yeah. So I'll let x be just lambda cross 0, and let y be mu cross 1. So this is this disjointifying trick. Is empty here. And for z, we'll just take lambda kappa itself. So we'll just steam through from this and derive this here. kappa to the lambda plus mu. So by definition, this is the cardinality of the set of functions from this into this here. Well, here's a set of size, this cardinality here. I kept kappa downstairs for not particularly sure why. Right. Now I'm using this here, that this is bijective with this, with z as kappa, right? Well, if these are bijective, right, they have the same cardinality, which is what I've written down here. So this is using this exercise here. The size of a Cartesian product, cardinality of a Cartesian product, so this is again by definition here. Right, so I take, if I've got product of two cardinals here, it's defined to be the cardinality of a Cartesian product of the things there in the product. There we have it, Cartesian product of these two things here. So this is definition of cardinal times here. And then this is kappa to the lambda, right? X is a set of size lambda, right? Because X just is that. Right? So kappa to the lambda is by definition here the size of a set of functions from a set of size lambda into a set of size kappa. And the same over here is kappa to the mu. So it says in the text using exercise 430, and that just means I can put any representative sets in of the same size, of the same size and get the same output. Right? So whether I write lambda or kappa here or x here makes no difference. So this gives us the first part one. Any questions or anything I should go over again there before we move on? Okay. Let's look at part two then. Kappa to the lambda to the mu is kappa to the lambda times mu. So again, if we look back at what 415 said, there's a clause there we want to use. 415.4. So there's a bijection between the functions from x into the set of functions from y to z and the set of functions from x cross y into z. Right, so we have sets of size kappa, lambda, and mu here. So definition of cardinal exponentiation here is, this is the size of the set of functions from mu into this set. Okay, this is a cardinal number. So I'll replace that with its definition as well. So this here has the same cardinality as the set of functions from lambda into kappa. Right, so this is an ordinal number. This is a set of functions. But they've got the same cardinality, right, by definition. And that's how we define what this is. Right? So I've just substituted in things of the same size, same cardinality here. Okay, so now I've got functions from mu into this set of functions, and I'll apply then the exercise here. So I'm going to say that this is the same as this Cartesian product into kappa. Okay, I just need to write these. I have things written down, and I just need to write this the other way around. This Cartesian product has the same size as this, obviously. All I've just done is switch around the x and the y coordinates, as it were, here. And now I use the fact that lambda cross mu, the cardinality of lambda cross mu here is lambda times mu, to write this down as kappa to the lambda times mu here. Using this, and the fact if I've got anything from cardinality of set of functions from A to kappa, this is kappa to, again, the size of A. Right, so A here is lambda times mu, right? And this is the cardinality of lambda times mu here. Sorry, Cartesian product, lambda times mu. It's got this cardinality. So that finishes 2. So someone asks, about the collection of functions. So this is by definition. This is a set of functions, f from y into z. And then they're asking about the nature of this. How can we write this down here? So, well, you just keep a cool head. This is just a set of functions, f, that go from x into this. This is a set. Can just as well be the range of a function as something like this. So these are both sets of functions. Okay. Right. We're going to omit Hartog's theorem. So 1461 to 1478. Okay, we just don't need it. So we'll save time by cutting it out. But we will take the corollary afterwards. Corollary 434. Okay, which is written as a corollary to Hartog's theorem, but actually we can prove the corollary without without actually using the theorem. So we write card. So this is defined to be the class of ordinals such that alpha is a cardinal. Right, so that means it is its own cardinality. Yeah. And the corollary says that card is a proper class. So the idea is, well, the picture is, here are the finites. Here's omega. Right, so these are all ordinals and cardinals simultaneously. Okay, then come some ordinals that are not cardinals. Omega plus 1, omega plus 2, and so on. You can see the statement of Hartog's theorem says for every ordinal, there's a larger cardinal. So for any ordinal here, there's going to be a larger cardinal. Okay, well, we can justify that anyway. So let's prove the corollary and then complete this diagram a little bit more fully. Suppose card were a set. So this is how, these proofs showing that something is a proper class always start out. They're usually proofs by contradiction, and you show that suppose it was a set, and then you get a contradiction. Right, so if it were a set, then the union of card here right, is a set. Well, any cardinal, right, is an ordinal. So it's a transitive set, well ordered by epsilon. A union of transitive sets is a transitive set. In fact, it's a union of ordinals. So actually, it's an ordinal. So I could have just said that straight up. It's a union of ordinals. So it's an ordinal. But actually, one of the exercises I said before said that so it's an ordinal. Okay. Call it tall, say. But by Cantor's theorem, the cardinality of the power set of tau is bigger than tau. There is no bijection between tau or any set X and its power set. So for any set X, X was injective into the power set of X, but not the other way around. So what is this? This cardinality is something bigger than tau. If tau were here, this would mean all the cardinals were below tau. But here is a cardinal number that's bigger than tau. So this is a contradiction. I mean, I suppose if I say a bit more here, what we've got is tau is injective into the power set of tau. So that implies...
Sorry, can you read the page down, please?
Sure. That is saying that tau is less than. So perhaps officially Cantor's theorem says this, and I'm using this consequence of Cantor's theorem here. As then here, this is a cardinal number. Not in card, which was supposed to be a subset of tau. So there's no such tau that bounds. There's no such tau here that bounds all the cardinals. For every tau, there's a larger cardinal. So I can use Cantor's theorem to say, for every ordinal, there's a larger cardinal. So this is finished here. So we use Cantor's theorem to show there is no largest cardinal. And in fact, there's a proper class of them, and they come all through the ordinals. So if in this diagram here are all the ordinals, these cardinals occur all the way up through the ordinals. Again, they're a kind of thinner, if you like, collection. There are many ordinals between every cardinal, but once you get up to the infinite ones, but the cardinals stretch all the way through the ordinals. So another corollary here, 435. For any set X, there's always an ordinal nu, so that there is no injection from nu into X. It's just too big. So I mean, we've already done this. It's just what we've said in another way. I could take nu to be the cardinality of the power set of X. So cardinality of X is less than the size of its power set, right? Which happens here because there's an injection of X into its power set, but not in the other way around. So there's no injection of this into this, right? We know there cannot be a one-to-one map of nu into X here. Again, this is Cantos theorem. Right? So what this does is give us a picture of the cardinals, again, which I had on the previous page. Again, the finites. And then we have the ordinals. And the cardinals are a subclass of the ordinals. So it's convenient to enumerate them. Well, once we've got past the finites, this is the first infinite cardinal. So we enumerate the infinite cardinals. So our friend omega here, it's the first infinite cardinal, or the zeroth, if you like. It's the one that starts off the enumeration of infinite cardinals. But then we saw that things like omega plus 1 was bijective with omega, and omega plus omega is bijective with omega. So these are not cardinals. So there are these ordinals in here are not cardinals. But then after a while, you reach the first ordinal that's not bijective of omega. And we call it omega 1. Right? So this is least ordinal, not bijective with omega. We do know there's a larger cardinal. That's what we've just been talking about. So there's a least larger cardinal here. We call it omega sub 1. And similarly, omega 1 plus 1 is bijective with omega 1, and so on. Omega 1 even here. But then there's going to be another cardinal beyond that, which is not bijective with the smaller ones. So this one we call omega 2. So the least ordinal, not bijective with omega 1. Right? So this is the least ordinal bigger than omega 1, least ordinal tau bigger than omega 1, which is a cardinal. And the picture then continues. Right? I just keep enumerating larger and larger cardinals. So there's going to be an omega 3 and so on. And then, of course, there'll be an omega n for each n, because there's no n to these cardinals. And when we get to, well, after we've enumerated all of these omega n's, we look at the supremum of the omega n's. We're going to call that omega sub omega. So we're going to define this to be omega sub omega. It's the supremum of a set of cardinals. So by an exercise, it's a cardinal. It's the least cardinal bigger than all of these. So it's kind of like the continuous limit of the smaller cardinals here. Right? Supremum, it just means the least ordinal bigger than all of those in the set. Well, it also happens to be a cardinal. So we'll enumerate it as the omega sub omegath cardinal. But the process keeps going. There's another least cardinal beyond that, which we're going to call omega sub omega plus 1. Right? And so on. So we formalize that all in a definition, 436. So we define by trans-finite recursion a kind of an enumerating function. Omega 0 is omega. And omega alpha plus 1 is the least cardinal bigger than the previous one. Right? So if I were to zoom in on this picture higher up, I'd have omega sub alpha here, and I'd have some omega alpha plus 1, the very next cardinal. So all of these ordinals in between, their cardinality is omega alpha. But then we reach one which I can't biject with omega alpha. And at limit stages in this recursion, like when lambda was omega, we just say this is the supremum of the previous guys. Here. Any questions about this picture? Now, one thing you have to bear in mind is that, look in textbooks and, in my notes here, because I want to get you used to it, is there's another system of notation for these people here, and that's to use the Hebrew letter Aleph, first letter of the Hebrew alphabet. So, and these are just entirely just synonymous, right? There's nothing else in it other than the fact that two systems have evolved. So this is Aleph 0 here, and this is called Aleph sub alpha plus 1. And this one here is, I'll try and draw it a bit better, Aleph lambda here. So I want you to be aware that there are these two synonymous notations for the same thing, and I'll use both without warning, right, to get us used to it here. Now, cardinals, infinite cardinals, right, just like the ordinals that index them, here they come in three flavors. They're either zero, the indices are either zero, successor, or limit. So omega 0, that's our favorite omega here. These are called successor cardinals, and these are called limit cardinals for obvious reasons, right, here. So any cardinal kappa bigger than omega is called uncountable. Because I can't biject it with omega, so it's not countable. So it's infinite and uncountable. And it's called a successor or limit, depending on where it sits. So if kappa equals omega alpha plus 1, for some alpha, it's called a successor cardinal. On the other hand, if it's the lambdath cardinal in the enumeration of the infinite cardinals, for limit lambda, it's called a limit cardinal. And I mean, a limit cardinal is always, of the form supremum of previous cardinals. Again, so to give its definition again, it's the supremum of the previous ones. So we can always get to the next cardinal by going one more step in our enumeration. So often kappa plus means the next cardinal after kappa. So in this notation, omega alpha plus 1 is the next cardinal after omega alpha. That means go up plus 1 here. So this sequence of omega alphas or aleph alphas here, the transfinite recursion we've got, we think of it as being an enumerating function. This is kind of the aleph function. It goes from ordinals to cardinals. Enumerates in strictly increasing order. the infinite cardinals. So we define f of Aleph alpha to be, as in that trans-finite recursion, it's omega sub alpha, or if you prefer, Aleph sub alpha here.